Thank you very much. Good afternoon. Just give me a minute to share my screen. Well, I would like to thank everybody for finding the time to attend this workshop. I do hope that it will be interesting to listen to and that you'll be able to learn something new. My name is Stanislav Zabodaev. I work in the MKS company in Zelenograd, Russia. I would like to tell you a little bit about transcranial electric stimulation. In my talk, I will give you an overview of this method, how to perform transcranial electric stimulation. I'll tell you about the methodology that we used, and I will do a short demo of our transcranial electric simulation. I'll tell a little bit about the devices that we make, and I do hope that I'll be able to answer your questions at the end. Our workshop will be a little bit more technical. So those of you who have never performed transcranial simulation, or those of you who have just embarked on this field of research, I think you'll be interested to listen to my presentation. Let me tell a little bit about the company that I work for. So the company is called Medical Computer System. We are located in Zelenograd. Zelenograd has been known as the Silicon Valley of Russia. And Zelenograd is really well known for the microelectronics industry. So in my company, we work on manufacturing different devices for research and medical use. So we manufacture EEG devices and consumables, TS devices and consumables. We manufacture things for the space station, automated pacemakers. So we sell our products in Russia and abroad. So let me tell you a little bit about transcranial electrical stimulation. So transcranial electrical stimulation is different from magnetic stimulation. Transcranial electrical stimulation is a non-invasive brain stimulation using weak electric currents. And the weak electric currents are delivered to the brain via the scalp. So what we do, we use a magnetic coil. The magnetic coil is put on the patient's head. It induces a short-term magnetic field pulse. This magnetic field is usually focused, and it is able to penetrate deep into the brain to induce electric current in the brain tissue. This can produce certain neurological effects due to the induction of electric current and the shift of electric activity in neurons. Navigational TMS provided an increase in the development of TMS itself, but the coils that are used in TMS are rather large, therefore it is a bit harder to aim the magnetic fields to target a certain brain location that needs stimulation. There is a certain gradient which is quite extensive, so we need to understand that TMS can be used to stimulate not just a certain brain area, but also all of the adjacent areas.
Now we get back to electric stimulation. Here we use special electrodes, and you put on the current generator, which keeps this current on by regulating the voltage potential differential between electrodes, two or several electrodes. And now we modulate neuronal activity of the brain, and we get certain effects. This is what I'm going to tell you about later in greater detail in terms of ability for academic application. They're also quite wide. We can treat depression and also clinical applications. You can treat strokes, Alzheimer, Parkinson's disease, and such neurological manifestations that are directly linked with some changes in the function of the brain. This procedure gives us pretty good results compared with a reference group. And for healthy people, we also try to use TES, transcranial electrical stimulation. And current studies show that it is possible to use this electric stimulation to increase the volume of the short-term or operational memory, some other cognitive functions, compared with the reference group that didn't get the stimulation. It's hard to talk about a specific universal device that would be commercially available that you could use as a university student to turn on some device on your head and improve your memory. This is not what we are talking about at the moment. This is just the initial stage of some major studies. But in terms of the clinical applications, there are relatively inexpensive devices based on that effect to treat migraine, for instance. This is a device with two electrodes that's put on your forehead. Then you stimulate the surface with electric current of impulse form, and it reports the mitigation of pain. There are reports about the mitigation of pain. And if we look at the previous slide here, on the whole, electric stimulations, and it's DC stimulations using direct current. That's when we have one cathode and one anode, and the current doesn't change during the procedure. Lately, there have been a number of studies with alternative currency or random noise stimulation, also with AC, with the spectrum distributed in some kind of band. It's like noise stimulation. For example, if you go from 0 to 300 hertz, in this band, you see no effect when we stimulate from 400 and up. You see some effects that we didn't see in the past. This is what is also used today in terms of stimulating with alternative current. You could, our bands, alpha, beta, gamma, theta, delta ones, and there's a separate study devoted to AC stimulations in the alpha range of 10 hertz and how the stimulation in this band would impact certain brain functions. In most cases, they of course use DC stimulation. That's a historical thing. DC stimulators are quite affordable and available, and it can be explained in terms of neurophysiology, and anything else is something exotic. There aren't that many publications about AC stimulation compared with DC one. As for the direct current, you can easily explain this effect in the following way. Neurons, much like any other living cell in the human body, has this certain transmembrane potential from -70 to -90 millivolts. This is the so-called current potential. When there's a nodal stimulation, when you put an electrode over the certain area of the blood which is connected to the positive pole of the electric stimulator, then the tissues under that electrode get the gradient of a direct electrical field, which sort of raises this potential of the resting state. Used to be -70. It moves to -60, -50, something like that, and in that sense, the resting state potential goes up for an entire group of neurons, and the adjacent neurons continue firing a specific neuron by action potential. And at the moment when total transmembrane potential crosses a certain border, this neuron fires. You increase the excitement of certain groups of neurons in the area under this anode or electrode connected to the positive pole. In other words, if we need to excite a certain area of the brain, we do a nodal stimulation, and vice versa. If you need to inhibit a certain portion of the brain, we introduce a cathode there and do the same. If we have two electrodes, if both of our electrodes are on your head, from that point of view, one part of the brain will be excited, another one will be inhibited. When you don't need this, we only want to excite a part of the brain, you can install cathode where there's no brain. In most cases, they put it over other areas on your neck, or even on your shoulder, or even over your mammillary process. And this is how we get the effect after the stimulation with direct current. As for AC stimulation, in this slide, there's a relatively fresh article in the Nature journal about the use of AC stimulation to treat depression. Both electrodes are on one's head, and they compare two options, stimulation with 10 and 40 hertz. And it's an interesting article, really, and there's a link in this slide. In the bottom left corner, there's a screenshot of the top of the article in Clinical Neurophysiology, an overview on transcranial stimulation with DC. And back then, there was a certain decision. There was a summary that in some cases DC works well, and some are doubtful. It definitely works when you need to treat different types of pain, migraine. It works quite well for depression, all sorts of dependencies and addictions. And this stimulation leads to generation of endorphins in human body. Thus, there's this replacement of this electric stimulation, using electric stimulation instead of smoking or drugs addiction. And this is how they're trying to deal with it. Now, this is about how it best works. And now a few words about technical details, where manufacturers of both equipment and the electrodes. Let me give you more details about it. What kind of electrodes can be used for TES? Usually it's stainless steel or special conducting a rubber, and you put it into salt solution and put it on one's head. And lately, you can use to the stimulation and registration at the same time. It can be done consecutively or simultaneously from the same electrodes. Fluoride silver-based electrodes that are currently used for EEG for recording. It's what we use, trying to use this AGCL electrodes. And in terms of science, there's no compromise. It's all about silver chloride, and silver chloride-based electrodes can be used for both, but as opposed to stainless steel, silver chloride is first of all a salt. Chloride is quite active, and when we add gel, current conducting gel, or some kind of electrolyte, and there's dissociation in the solution of silver chloride into its components, you get ions of silver and chlorine. And my slide, there are two pictures on the left and right-hand side, electrodes before and after transcranial stimulation. The top electrode was connected to the anode and the bottom one to cathode. What happens when we stimulate one's brain with DC? On the anode, silver oxidizes, and then it interacts with hydroxyl group ions, and you get this residue, silver hydroxide, which is unstable, and that it dissolves into silver oxide and hydrogen. And silver oxide is stable enough, and it has this dark gray color that you can see at the top right, in the top right corner. and you get this gray color. And there's an opposite situation with the cathode. Free ions of silver are recovered back to silver, and are left as a residue on the conductor. And looking at two pictures, you can see that the anode oxidized, and there was recovery of silver on the cathode. There's more silver actually there. The problem is when we use DC stimulation with significant currents, usually we use 2 milliamperes, but they also, that's in the scientific articles, and they use different electrodes. Usually it's the area of 35 square centimeters, fairly large items, and they use 2 MA current. But it's quite powerful, but it's not silver chloride. And what might happen, and in our case, we use these silver chloride electrodes, and I chose on my device DC stimulation, and this electrode lasted for no more than 3 minutes, but your stimulation needs to run for 30 minutes. This is what happened to silver chloride electrode. Its impedance went up. It no longer conducts current. You cannot use for stimulation anymore because there's no silver at the top. So silver chloride is not really useful here. When we register EEG, there are very insignificant currents of nano amperes, but it oxidizes slower. But here we oxidize it on purpose. What can we do in that situation? Some manufacturers like Neuroelectric claim that their silver chloride electrodes can be used for up to 10 hours. It depends on the level of your DC, on the power of your DC. If you use AC, then our electrode oxidizes half a period, and then for another half of the period it is recovered. So it works very well for AC, but not for DC. If you use strong currents, the electrodes will quickly degrade. You need to use either very small currents of microamperes of 100, 200 MA up to 500, and then it will be below. There will be oxidation, of course, if you use the same electrode, but the entire overall lifetime of the electrode will go up. Let me give you an example.
We have clients who work with children, and they use our standard EEG electrodes, the NTC electrodes. And the diameter of the chloride silver disc is only about 6 millimeters. Therefore, when they use 100 microampere stimulation with direct current, they noticed that the electrodes have shown degradation in after about 20 hours of stimulation. So they were quite long lasting. The rest, when it comes to the lifetime of an electrode, it comes down to the type of current used, the surface area of the electrode, whether it is coated with the chlorine silver paint or whether the paint is integrated into it. But however it may be, if you need to use a direct current for stimulation, it's better to use either stainless steel electrodes or electricity conducting rubber. If you need to use alternate current stimulation, then silver electrodes can be used to acquire EEG data. There is another thing that I wanted to mention when it comes to the structure. All types of electrical stimulators are quite simple. A stimulator is essentially a direct current generator. So a stimulator needs to maintain a preset voltage, let's say. A generator works at a certain power load. And what is this power load? Basically, this is transelectric impedance. If the electrode is not connected well, then the impedance will be higher. Therefore, an electrode might become dysfunctional, generate won't be able to increase the charge, and therefore all of the electrodes will stop functioning. If you use, let's say, a regular stimulator, let's say a Chinese-made stimulator, it will work for some time, but not all of them can deal with electrical overload. So when we are talking about the DC generators, they usually have a maximum voltage threshold. So in order to estimate whether the electrodes have been placed correctly and whether the following stimulation will be successful, you can do that with an impedance meter. If, let's say, we're using DC stimulation, just like in my picture that you show on the screen, say one anode, one cathode, and if you calculate the sum of all of the impedance values for all of the electrodes, it should be less than the value that you can see on the screen. We can use Ohm's law to perform this calculation. And if, let's say, the maximum voltage of a generator is 30 volts, then impedance should be less than 15 kilovolts for 2 milliamperes. It is quite easy to reach this value if you're using small surface area electrodes. Then you need to pre-treat the screen with abrasive scrubs. There are different market options available. Then you need to apply a conducting gel or paste. Or you can use cotton sponges soaked in saline. Well, this is the most common way to apply the electrodes, but I believe that gel is more beneficial. It can maintain its shape in an easier manner. It doesn't dry up so quickly. And especially if you're talking about long-term stimulation, let's say 30-minute stimulation, the saline solution might dry up. Therefore, there will not be a tight contact between the electrode and the skin, which in turn will lead to a change in local current density. Let's say if a cotton sponge dries at its edges, it will not be very comfortable for your patients. Transcranial electric stimulation is sometimes reported to cause a prickling sensation in patients. And I've even heard that some people use a method to determine the maximum value, the maximum allowable power of the current to be used for each patient. I've heard that some researchers gradually increase the current voltage and they ask the patient to tell them when they start to feel prickling. So if a patient reports a prickling sensation, then they decrease the voltage of the current. So basically it is a trial and error methods. And that is something that we've seen in a clinical setting. But if we're talking about research, of course, we need to ensure reproducibility. If the research specifies 2 milliamperes, then each subject should receive 2 milliamperes. So that wouldn't be acceptable. Let me apologize for this slide. It is hand-drawn. I didn't have enough time to make it prettier. There is a misconception that seems to be quite widespread. Some people believe that if you connect to galvanically decoupled current generators, then you might be able to instantaneously stimulate the brain in the same fashion that you would have achieved using two separate electrodes. Well, this is not true at all, and it is not true because well, there is the Ohm's law, as you can see on this picture here. The researchers wanted to stimulate an area of the brain located under the F3 electrodes using the 1020 system with a contralateral localization of the cathode. The second generator was to be placed under the T6 electrode before the memory process on the contralateral side. Had both of these generators run independently, then we would have had one anode, one cathodes, one input, one output area. But the minute we connect the second generator, then these generators become galvanically coupled through the patient's skull. So if you talk about the sensor will show you that there is a current flow and it will seem fine on the surface, but what will happen in reality is the redistribution of the current. And this redistribution of the current will be completely unpredictable. For instance, the first generator will generate the currents for the electrode above it, and some of the current will be directed elsewhere. So the anode-cathode connection based on the voltage of the current might lead to a situation when the stimulation will either worsen, as in this example that you see on the screen. In this instance, we wanted to use 60 milliamperes for stimulation. 60 milliamperes is not a significant value, but we wanted to use 60 milliamperes to stimulate a certain brain area. But in reality, because of the second generator, we stimulated this location using 37.5 milliamperes. And there was another example when we wanted to use 30 milliamperes, but because of the second generator, we ended up using 7 milliamperes, which is pretty much negligible. So I believe that it would be pertinent to use just one generator, which should be commutated to several electrodes. So if you need to stimulate, let's say F3 and T6, Then you can connect the anodes to F3 and T6, and you place a cathode more remotely. That is another technical issue that I wanted to raise. In this part of my talk, I would like to demonstrate our NVX36T device. You see the list of technical characteristics of the device on the screen. It uses one current generator that can be connected to 3 channels. It can be used for flexible EEG acquisition. So it is a 32-channel EEG stimulation with direct current, alternate current, direct noise stimulation. And a lot of researchers now can use both DC and AC stimulation, which are applied at the same moment in time. Let me show you what the stimulator management software looks like. It is called tDCS Expert. So using this interface, you can control inter-electrode impedance. And let me show you how it works, especially taking into account all of the constraints that I had talked about. Let's say we wanted to stimulate FP1. Let's put an anode to FP1 and a cathode to FP2. Here we can also evaluate earth impedance. This is just a schematic. We didn't use it with the real subjects. That's not something that we need for the demo, but if we want to use a direct current stimulation between FP1 and FP2, then we just do the addition of 10 kiloohms to 10 kiloohms. Therefore, we have the impedance set at 20 kiloohms. Therefore, we cannot use 4 milliamperes to stimulate the brain. So this is the impedance meter mode. So here we can do EEG acquisition, and this software is very simple, very user-friendly. So we launch EEG acquisition, and the data is sent directly online. So if you have a client software that is able to extract data, so basically what we're getting is raw data from EEG, then direct current stimulation. Let's say I set this option that I had mentioned previously, so direct current stimulation, one anode, one cathode. So we can connect the anodes here and the cathodes here. And we can place them like so on the patient. So we put on the EEG cap, apply the gel, and so on and so forth. Then we select the current, so we can use the drop-down menu, or we can enter it manually. Let's say 1000 milliamperes. So there is also the soft mode, so the soft start mode, that is required to give more comfort to our patients, and so we do not discommode them. When we use the DC stimulation, if we were to give our patients all of the voltage at once, so then the patient will see a sharp burst of light. So there is a very sharp shift in potentials. It's not something intrinsically bad, but it is a bit uncomfortable, so we can increase the voltage gradually. So I've started the stimulation. You see that the voltage is on the rise. There is a cyclogram on the bottom, which is showing us a correlation between the current used and the inter-electrode impedance. So the software monitors the situation, measures approximately 21 kilo ohms under the electrode. If, let's say, there is a break in the electrode connection, the overload alert will pop up on the screen, which is needed to ensure the quality of the procedure. If we're using long-term stimulation, that is absolutely mandatory. Following this, when the stimulation is complete, we need to evaluate the quality of the stimulation. So all of the data is uploaded to a file that we can use to evaluate the quality. There is also a sham mode. That is something that is needed for clinical trials or for research. So we trick the patient. Let's say there is no stimulation of the brain, but the patient believes that they are receiving the stimulation. If you're using the sham mode, we also have a gradual voltage increase, so the patient will feel a prickling sensation, and after that, the stimulation stops. As you can see, the generator is off right now. Then at the end, you will have a certain period again when we do apply direct current so that the patient believes that they have undergone a stimulation procedure. I see that I do not have a lot of time left, maybe about 10 minutes or so, so let me finish with the software demo and then I'll be answering your questions. Okay, I think it's pretty much clear when it comes to DC stimulation. Let us switch to AC stimulation. Let's say we want to replicate the same mode that I showed you in this Nature article. Let's say F3, F4 connected to the anode, TZ connected to the cathodes, and we use 2 milliamperes in total. So F3, F4 anode, CZ is cathodes. So sine 10 hertz. Let's say I set time at 1 minute. So that is how it will be visually represented. Again, we have a gradual increase in current voltage and we'll be using AC stimulation. Here is the peak current and right next to it is the recalculated effective current value. And in order to evaluate the quality of the procedure, the software will measure the real current value. See, I switch off the F4 electrode, so all of the current is going through CZ10. But of course, during the procedure, we need to ensure that we have approximately the same current value in all of the electrodes. So the software is showing you an increase in the voltage, and the voltage value remained the same in accordance with the preset value. In the top right-hand corner, you see the generator control window, which shows you what's happening with the generator. This is the signal that the patient receives as a stimulating signal. So using this window, you can monitor it. We also have the soft and the sham modes for the AC stimulation in the same manner we had for the DC stimulation. Also, we can select different impulse shapes, for instance, square, ramp, trap, random. Let me show you the random stimulation, which I had mentioned previously. Here you can select the range for the random noise filtration, and the rest will be the same. Let's see what it's gonna look like. So that's how it looks.
And there's a signal right now which looks like noise. There's this random noise simulation. You can upload a file from elsewhere. You have a substandard form of impulse. You can upload another file and play it, even if it's music. This is a song of one of the Russian music bands, and let's see whether this will be efficient. Let's see whether this treatment will be efficient. In top right-hand corner, you see the data for the music. It doesn't mean that you sort of upload music directly into the brain. It's all compensated by the brain capacity. This will be the analog stimulation by accidental noise, but it's just for demonstration of what this mode can do. And this is the alternative current monopolar stimulation, ACM. And here we introduce some offset, and you can set the peak current. Let me turn this off. And this is how it looks like. Peak. The peak will be at 500 microampere, and here the offset is 1 microampere. So there's a separate mode of setting a profile for double line study when we need to provide data not just for the patient, but also for the nurse that's going to perform the stimulation. And there's also the mode of sham stimulation. We, for example, this password 1, 2, 3, 4, 5. We save it. Then we select the name for the profile for double line stimulation. Let's say it's depression. We save it. And then when we select a profile, it's double blind, and this is what we see. The nurse came and she was told to use this profile for this patient. She sees F3 to channel 4, F4 to number 6, and CZ to number 10. You control the impedance, and then you turn on the stimulation. And now the stimulation is on. At the top, you get the time left until the end of stimulation. The nurse doesn't really know whether the real stimulation is on or not. I Click off CZ electrode. If it was not well connected, you will see that alarm. I basically ran out of time. It's 5 minutes left until the end of the workshop. I don't want to hold on too much of your time, and I will be ready to take your questions.